Alright, today's video lesson is on the collision theory. What we're going to look at is an explanation for all of these rate laws that we've been looking at so far. Um, so if you remember, a law is just like any other law that we talk about in science. This is just a regular law that says that if I increase the concentration, my rate goes up by a certain factor, some sort of factor n and m, based on what we talked about for figuring out differential rate laws. And that's it. It just tells us what happens. It doesn't tell us why anything happens. So what we're going to do is we're going to come up with what's known as a collision theory. Now, in science, the word theory and model are used as a pretty much the same thing. So our models are our theories. So we can interchange these two words. So this is a theory for kinetics or a model for kinetics. Okay. So our models are a way of explaining things. So we know that the concentration has some kind of effect on the rate. Okay. We're going to talk about why that is in a little bit. But we also know one other thing. We haven't talked about this, but we also know that temperature can also change the rate. Now, if we look at changing temperature, we don't change the concentration. So our concentrations don't change when we change temperature. So therefore, when we talk about changes in temperature, we have to be talking about changes in K, right? That's what's going to change the value of K. Now, if you remember in equilibrium, we had talked about K changing. So these two Ks, the K in equilibrium and the K in our rate constant, in our rate expressions, are going to be connected together. They're not exactly the same, but there is a connection. If you go back and watch the beginning of the equilibrium, you can see the connection between the little k and the capital K. Alright, so why is it, what's going on here? How is it possible that that K is changing? Well, from experimental data, we can see that as K changes, as we change temperature goes up, and we keep determining new values of K, we can see that K keeps changing and changing and changing. So for most experiments, as temperature goes up, K goes up. And if K goes up, right, if there's an increase in K, then there has to be an increase in the rate. Okay? So that's what we're looking at. So those are two things that are going to change, concentration and temperature. And I'm going to come back in another lesson and we'll talk about all of the things that can affect the rates. Okay? And we'll talk about why. Alright, so here's our first part of the collision theory. So first of all, what the collision model is, or the collision theory is that in order for reactions to occur, molecules must collide together. That's the basic premise. It's a relatively simple model. It just talks about the fact that in order for two particles to react, they have to come together. So it makes sense that if hydrogen is going to react with oxygen, they can't do it here, right? Because they're far away from each other. They literally have to come in contact with each other. The H2 has to collide with the O2 in order for a reaction to happen. So they actually must come in contact. All right. And this is based on the kinetic molecular theory, the fact that the particles are moving around, so the fact that they have motion is going to tell us why they're going to obviously react. So that makes sense. If you think about solids, we don't really see many great reactions in solids because of the fact that the solids particles are kind of stuck together and they can't move around too much. Liquids, they kind of flow around so we can get the mobility of particles. That's what chemistry's done as a liquid science or an aqueous science, because we get the particles to move around and collide. Gases would be great because gases will collide. They're at the highest kinetic energy for them, and they tend to collide most often and give a lot of reactions. So a lot of good reactions happen in gases, and some pretty good ones happen in aqueous environments. So the greater the number of collisions, the higher the rate. So it's really this simple. If we want to increase the rate of reaction, we increase the number of collisions. We want those particles to collide more often. So if we know that at a higher concentration, there's a higher concentration of our reactants, then if there's more of the particles in there, we know that there's going to be a higher frequency of collisions. It makes pretty good sense, doesn't it? More concentration, more particles, higher number of collisions. If I increase the temperature, what's going to happen is a couple things. First, I'm going to increase the kinetic energy, and which will lead to more frequent collisions. So by increasing kinetic energy, not only do I increase the collisions, but I also increase the magnitude at which they smash together. So there's twofold here. Not only do they collide more often, but they collide with more energy. And that's different from the first one here. Because if I increase the concentration, I'm not going to increase the kinetic energy. Remember, increasing kinetic energy increases temperature. Okay? Alright, so that's the basic premise. Alright, so let's take a look at this. Now, Savant Arrhenius found in the 1800s that it's not just about the particles colliding. Because if particles just collided together, then every reaction should happen already. So think about it. Trees in the forest are constantly being collided with oxygen. So why isn't that the oxygen doesn't cause all of those trees to just instantly burn down? Well, because it's not just the fact of the oxygen colliding with the tree that causes it to burn down. There also has to be a minimum energy required to make the reaction happen. So when the particles collide, when that oxygen collides with the tree, it could cause a bend or a twist in the molecules, or it might just bounce off and not do anything at all. But if it can bend them and twist them and eventually break them, then a chemical reaction can happen. If not, otherwise it just bounce off and nothing happens. So right now you're a carbon-based just like the tree, and you don't burst into flames when you're immersed in oxygen, but there has to be that activation energy. So even if you're in a concentrated room full of oxygen, you're still not going to blow up because you need that higher temperature or something to overcome the minimum energy needed to cause a reaction to happen. Okay, so to get the reaction to happen, you need to have the kinetic energy of the collision to be equal to or greater than the activation energy. All right, so it's not just that they collide together, but they collide with enough impact that they can cause a reaction to happen. Now, this is a very typical diagram that you'll see on the AP test, talking about reaction pathways. So over here, don't worry about this thing here. This is more complicated stuff. But over here, you were just going to say, in general, we start with our reactants. So over here, for the reactants, let's say are hydrogen and oxygen. So these two things are going to come together to create a reaction. Our products should be water. Okay, so over here we have our products. So these are what are going to form. And our products, in this case, are going to be just going to be the water. So over here we're going to try to form water, and over here we're going to have hydrogen gas and oxygen gas by itself. All right, what they're going to do is this represents the pathway. Now notice the energy here. This is the energy of our reactants. This is the energy of our products. Now you can clearly see that the reactants have more energy than the products do, right? Reactants are above the products on the scale. So, reactions tend to go towards lowest energy possible. Okay, that's just the way reactions go, kind of like water going downhill. Reactions tend to go towards the lower energy possible. We're going to talk more about this in thermodynamics in the next unit, but that's just the general progress. Now, the problem here with this reaction is that the reaction can't just go directly to the products. It has to actually overcome this bump in the data. So with this here, this EA is our activation energy. So we abbreviate this EA. And this is the energy needed to make the products form. So in order for hydrogen and oxygen to create the products, they have to overcome this activation. Now if I had hydrogen and oxygen in the room, they're not going to react together. They're just going to bounce off of each other and not much is going to happen. But if I allow them to collide together at a higher temperature, I'm going to cause the activation energy to go up because the particles are moving with more speed. They're going to collide more often and with a higher activation energy because the collision is going to have more energy because of the kinetic energy that's there. So the particles can then form the products. Now at the very tip of this is what's called the activated complex. With the activated complex is if you have hydrogen and oxygen coming together, that would be your activated complex. It would be this in-between state before having products and having reactants. So they smash together and they create the activated complex. Now this is the tipping point. Either the products form or it goes back to the reactants depending on how much energy there is. So it's kind of like putting a ball up a hill. You can kind of get the ball to go up and then back down. Up and then back down. If you hit it just enough energy, the ball can go boom all the way over and you can form the products. So once it gets over this barrier, it's all downhill from there for the reaction and it produces products. One other thing you want to take note of is the difference between this and this. This change in energy is the energy that comes out of the reaction. So this would be exothermic because we're losing energy, right? We start off with this amount of energy and afterwards we now have this energy. So this difference in energy, this change between here and here, is the amount of energy that comes out of the reaction. We would say this is exothermic. Now you could see a reaction that looks like this where the reactants are lower in energy and the products have more energy. Okay, this would be considered an endothermic reaction. So if we have one that looks like this, we would say it's endothermic. This is the energy that needs to be added to get the products to form. It'd be kind of like going backwards up the hill in this particular reaction to get water to form into the products or back into the reactants. Okay, so that's a very common thing to see on these types of problems. Okay. So where does this energy come from? Well, it comes from the energy in the particles, right? At every temperature, there's a certain amount of kinetic energy that the particles have, energy of motion. So if those particles are moving around, they're obviously going to collide together. So this chart here kind of shows the connection between higher temperatures and lower temperatures. This here is our minimal threshold, so this is the activation energy. So at higher temperatures, what we're looking at, this is a relative scale. So this is the number of particles that have this kinetic energy. That's what temperature is measuring. So this is the average particles that have this temperature, okay, or they have this kinetic energy. That's what temperature is. It's an average kinetic energy. So most of the particles have this energy. Now, not all of them do. Some of them have higher kinetic energies, enough kinetic energy that they can react together. So as temperature gets higher and higher, it kind of flattens out. We end up getting more and more particles that have the energy needed to cause a reaction to happen. So at higher temperatures, we have more and more particles that can actually form it. Take a look at T1 here. Not many particles can actually go into the reaction. So at a lower temperature, a small amount will be, and a lower temperature, even smaller numbers. Okay. So where does the energy come from? It comes from the essentially whatever temperature it's at. So at higher temperatures, we can increase that kinetic energy. All right, let's see if we can wrap this up here, because there's one more thing we need to talk about, and that last thing is that not only do the particles have to collide together, not only do they have to have enough energy to react, but they also have to have the correct orientation. They have to be arranged the right way. So what we have here is a molecule. There's a red one, and there's a blue one here. It's kind of, if you can see it, but I don't know how good your computer's colors don't really shine here. But let's say that these are green and green, and so in order for this to react, those two green ones have to react so that they can form the products. Okay, so if these are orientated in just the right way when they collide, then the activated complex is what this is, will then form into the products if there's enough energy for the collision to happen. Now notice here the green one is up here, and the other green one is here. Now they're not orientated together, so the green and the green can't come in contact, so the green and the green will not react together, and therefore no reaction happens. It goes right back to the way it initially was. Okay? So there's three things that you need to have happen in order for a reaction to occur. One, the particles have to collide together. Two, they have to have enough energy for the collision to occur. And three, they have to be in their correct orientation. Now be very, very careful when you are answering questions pertaining to the collision theory. If they ask you at all, why does a reaction increase its rate? If I increase temperature, why does the rate increase? You must reference one of these 3 points. You need to talk about these three. These are very, very important. So you have to say, according to the collision theory, the higher concentration causes more collisions to occur because there's more particles in the container. Higher temperature causes the kinetic energy to go up, so therefore when they collide with more energy to overcome activation energy, and because they're moving faster, they collide more frequently. Okay, so make sure you mention one of these three. This one is not too important, that last one. I mean, you really don't do much with that one in the AP test, but you should be aware of it. Alright, I'm going to end here today, at least with the intro to collision theory. In the next video lesson, I'll kind of talk about all the various ways that we can increase the rates and kind of address some of these 3 postulates or 3 points of the collision theory. Alright, I'll see you later, guys.